Today we are going to do a lesson on molecular orbital theory. What we will do in this lesson, there will be an introduction to molecular orbital theory. There will be an introduction to linear combination of atomic orbitals, or LCAO. Draw molecular orbital diagrams for s orbital and p orbital. Use notations to write molecular orbital energy levels. Apply common rules for filling electrons in molecular orbitals. Illustrate molecular orbital bonding for some molecules that are listed here, and explain some of their magnetic behavior. Predict the stability of molecules by calculating the bond order. Key terms you will use in this lesson: LCAO, or linear combination of atomic orbitals, orbital wave function psi and psi squared, bonding molecular orbitals, antibonding molecular orbitals, bond order, and paramagnetic behavior. This lesson is discussed based on the fact that you would have studied quantum mechanical model of the atom, understand the concepts of orbitals, orbital wave function, dual nature of matter, the Aufbau order, Hund's rule, Pauli's exclusion principle, and the system for writing electronic configuration using the quantum mechanical model of the atom. Molecular orbital theory. Molecular orbitals are formed by the linear combination of atomic orbitals, or LCAO. This model proposes that when two atomic orbitals combine, they form two molecular orbitals, one bonding and the other antibonding molecular orbitals. Bonding molecular orbitals have lower potential energy than the atomic orbitals and a higher electron density between the two nuclei of the molecular orbital. Similarly, antibonding molecular orbitals have higher potential energy than the atomic orbitals and lower electron density between the two nuclei in the molecular orbital. This is a basis of formation of molecular orbitals or diatomic molecules between similar atoms or different atoms. Here we are going to see the linear combination of atomic orbitals when s orbitals combine or p orbitals combine. We just take a quick look at the orbital approach to it, just to get an understanding of how the electron density changes in the bonding and antibonding molecular orbitals. The energy is supposed to be increasing when we are moving from the bottom of the page to the top. Here we are considering two atomic orbitals, 1s and 1s, from two different elements. These two orbitals are going to combine to form a molecular orbital. If there is an orbital overlap, this is how it may look. The first possibility is for the bonding molecular orbital to occur. There will be an increase in electron density between the two nuclei. There will be a lowering in energy for the molecular orbital in comparison to the 1s orbitals. And we use the notation sigma 1s to represent the molecular orbital energy level. Since this is a bonding molecular orbital, we also have an antibonding molecular orbital. The electron density between the two nuclei is minimal. This is designated sigma star 1s. So we have two molecular orbitals, sigma 1s, which can hold two electrons, and sigma star 1s, which can hold two electrons. Interestingly, the 1s orbital, like you already know, can hold a maximum of 2 electrons, and therefore if you have 4 electrons between the two 1s orbitals, they can be distributed in two molecular orbitals, 2 in the bonding molecular orbital and 2 in the antibonding molecular orbital. This is the orbital diagram for the linear combination of atomic orbitals between two 1s orbitals. Now we will look at the combination of p orbitals. Again, the energy is going up from bottom to top. We are taking the px orbitals. Px orbitals from two different atoms having similar energy. And these orbital overlaps are going to be axial along the same axis. Again, it forms a sigma bond for that reason. When this happens, it forms a bonding molecular orbital where the electron density between the two nuclei is pretty high. We call this a sigma 2px for the axial overlap, and it will have a corresponding anti-bonding molecular orbital where the electron density between the two nuclei is going to be less. This is referred to as sigma star 2px. Again, in the px orbital, according to the earlier rules that you have studied, there will be a maximum of 2 electrons possible. So if you have two px orbitals, there are 4 electrons, and these 4 electrons can be distributed in the sigma 2px and sigma star 2px. So the number of electrons in the atomic orbitals and number of electrons in the molecular orbitals will be the same. In the third case, we are going to look at the p orbitals that are going to overlap between each other by a sideways overlap or lateral overlap. So these are pi bonds when they undergo overlapping. Now there are 2 lateral overlaps possible between the py and py of the two p orbitals, and also between the pz and pz. So it's going to be exactly the same for the pz, and the energy for the bonding molecular orbital and the anti-bonding molecular orbital are going to be exactly the same. So if the py orbitals undergo a bonding, then it will change into the bonding molecular orbital as represented here. It's called pi 2py because it's a lateral overlapping, and it has a similar bonding taking place in the pi 2pz level. So we have 2 lateral overlaps between the py and the pz forming the bonding molecular orbital. They both have the same energy, but I've only shown the representation of the py orbitals undergoing a bonding molecular orbital formation. Similarly, they can undergo an anti-bonding molecular orbital formation where the electron density between the nuclei is much less, and they are called pi star 2py, which is also the case for the pz overlap, which is pi star 2pz. The pi star 2py and pi star 2pz has higher energy than the atomic orbital. The pi 2py and the pi 2pz has lower energy than the atomic orbital. So again, 2 electrons in pi 2py and 2 electrons in the pi star 2py, making it 4 electrons in the molecular orbital, which are coming from the py and py of 2 atoms which are forming the molecular orbitals. We will arrange them all in the increasing order of energy, and we can make a representation like this. We have 2 atoms, atom 1 and atom 2, where we represent the atomic orbitals. Here we have the 1s orbitals from 2 atoms undergoing bonding to form 2 molecular orbitals, sigma 1s and sigma star 1s. Here we have not drawn the orbital configuration, merely using the notation for the bonding molecular orbital and the anti-bonding molecular orbital. Once the 1s orbitals are combined, we have the 2s orbitals again forming sigma 2s and sigma star 2s. They are very similar. The only difference is the radial probability curve shows different values, and therefore the size of the orbitals are different. Again, we will look at the p orbital. Like I already said, there will be 1 axial overlap and 2 lateral overlap. So the px on the left and the px on the right combine to form sigma 2px as illustrated here. And the antibonding molecular orbital has a correspondingly higher energy, which is sigma star 2px. 2py and 2pz, they undergo lateral overlap like we had seen in the previous slide. They form pi 2py and pi 2pz bonding molecular orbitals, and the corresponding antibonding molecular orbitals are called pi star 2py and pi star 2pz. Notice that the energy of the pi star 2py and pi star 2pz is less than that of the sigma star 2pz. This is the molecular orbital configuration for a regular atom. Now here we are looking at atoms having a maximum of 10 electrons. Therefore, the maximum number of electrons that can be accommodated in this molecular orbital is 20. Now, instead of drawing the diagram that I've drawn on the previous slide, we can also write it merely by using notation. This is also arranging the orbitals in the increasing order of energy, similar to the Aufbau order in the atomic orbitals. We call it as sigma 1s2 because s2 represents 2 electrons maximum in that orbital, is less than sigma star 1s2, which is an antibonding molecular orbital. Again, the energy is less than sigma 2s2, less than sigma star 2s2. All the asterisked orbitals are antibonding molecular orbitals, followed by sigma 2px2, which is less than 2 orbitals that have the same energy, that is pi 2py2, which is equal to pi 2pz2. That is less than pi star 2py2, which is equals to pi star 2pz2, which is less than sigma star 2pz2. So this is the electronic configuration for diatomic molecules which have electrons less than 20 or 20 or less than 20. The energy increases from left to right. Filling molecular orbitals. The rules for filling the molecular orbitals are similar to the atomic orbitals in quantum mechanical model of the atom. The orbitals are arranged in the increasing order of energy. Hund's rule of maximum multiplicity is applicable. If you're not familiar with it, please go back and refer to it. Pauli's exclusion principle is valid. And the most important aspect is we can use the molecular orbital theory to interpret properties exhibited by molecules like magnetic property and write an appropriate configuration. Most of the time, a theory supports an experimental observation. We can calculate the magnetic moments for many of these diatomic molecules, and what we find is that we are unable to explain their magnetic properties by using valence bond theory. On the other hand, molecular orbital theory is capable of explaining the magnetic property of many of these diatomic molecules between similar atoms or between different atoms. That is one of the important successes of the molecular orbital theory. We can also explain resonance very easily, explain the concept of delocalization in benzene-like molecules, and those can only be explained using molecular orbital theory and not with the valence bond theory. Bond order. We can calculate a value called bond order using the equation half into bonding molecular orbital electrons minus antibonding molecular orbital electrons. If the value of the bond order is positive, the molecule will form. If the bond order is 0, the molecule will not form. A high value for bond order indicates stability. Whole number values for bond order represents the number of bonds between the two atoms. Writing electronic configurations, we're going to take a couple of examples here and write the electronic configurations and see how we can use molecular orbital theory for explaining their properties. First, we will look at the formation of hydrogen molecule. we have two hydrogen atoms, atom 1 and atom 2 on the left and right, extreme right. In the middle we have the hydrogen molecule. So we will write the electronic configuration of the atoms first on either side. We have the atomic orbital 1s1. Hydrogen atomic number is 1, therefore the electronic configuration is 1s1. On the left and the right you have that, which means we have one electron each in the two hydrogen atoms. Now they're going to combine to form two molecular orbitals, and then the electrons go into the orbital with the lower energy first, and then they go to the higher energy. So here it forms two molecular orbitals. One is sigma 1s2 and the other sigma star 1s2. Since we only have two electrons, they both go into the sigma 1s2 molecular orbital, which has lower energy than the atomic orbitals. So the electronic configuration of hydrogen molecule using molecular orbital theory is sigma 1s2. Now we can calculate what we call the bond order. Half into number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbital. In the bonding molecular orbital we have two electrons. In the anti-bonding molecular orbitals we have no electrons, which makes it half into 2 minus 0, which is equals to 1. Or we can say, since the bond order is 1, there is a single bond between two hydrogen atoms. The value is positive, therefore the molecule does exist. These are two things that we can say regarding the molecule that is formed using the molecular orbital theory. We can also predict the magnetic behavior. If a molecule has unpaired electrons, then it can show paramagnetic behavior. In this case, it will not exhibit any magnetic properties. Formation of oxygen molecule. Again, we have two oxygen atoms, oxygen 1 and oxygen 2. We are going to take the first electron in the s orbital, 1s2. On both sides, both oxygen atoms have two electrons in the first energy level, which is 1s2 and 1s2, making it 4 electrons for the two oxygen atoms together. When they form the bonding molecular orbital, 2 electrons go into that level because it has got lower energy, and the remaining 2 electron goes into the anti-bonding molecular orbital. That's what we see here. Again, if you go into the 2s level, which is what is represented here, there are 4 electrons in both of them together, and they go into the sigma 2s2, sigma star 2s2, filling the s orbitals and the bonding and anti-bonding molecular orbitals that arise out of it. Finally, we have the p orbital, where we have 4 electrons. Because the atomic number of oxygen is 8, we already have 4 electrons here. The remaining 4 electrons will be filled into the p orbital. So oxygen atom number 1 has 4 electrons, oxygen atom number 2 has 4 electrons, and first the sigma bond is formed, or the axial overlap takes place, which means the px and px will undergo overlapping to form sigma 2px. So 2 electrons will go into the sigma 2px. The remaining 4 electrons will go into the pi 2py, pi 2pz, and we have 2 more electrons remaining, which goes into the pi star 2py and pi star 2pz. I know I didn't label it here deliberately. Now we will label the atomic orbitals. You will see the electronic configuration 1s2, 2s2, 2px2, 2py1, 2pz1. Now we will label the molecular orbitals, which I've done on the right side of this page. So the lowest molecular orbital would be sigma 1s, and there are 2 electrons in it, therefore it's written as sigma 1s2. The next molecular orbital is sigma star 1s2, followed by sigma 2s2, sigma star 2s2, sigma 2px2. Then you have the py and pz, both holding 2 electrons each, and the energy of those 2 orbitals are the same. Finally, we have the last 2 electrons 15 and 16, that it goes into the pi star 2p y1 and pi star 2p z1. That would be the molecular orbital electronic configuration for oxygen atom or oxygen molecule. Now we can also write the molecular orbital electronic configuration like this. Sigma 1s2 is less than sigma star 1s2, is less than sigma 2s2, is less than sigma star 2s2, is less than sigma 2px2, is less than pi 2p y2 is equals to pi 2p z2, is less than pi star 2p y1 is equals to pi star 2p z1, which also implies the pi star 2p y1 and pi star 2p z1, they have one electron each. So oxygen is paramagnetic because of the presence of the two unpaired electrons in the pi star 2p y1 and pi star 2p z1 molecular orbitals. So we can safely say oxygen is paramagnetic, and experimental evidence shows that oxygen exhibits a paramagnetic behavior. And now we have a theory which can explain why oxygen exhibits a paramagnetic behavior. We are going to use this electronic configuration to calculate the bond order in oxygen molecule. Bond order is equal to half into number of electrons in the bonding molecular orbital minus number of electrons in the antibonding molecular orbital. Interestingly, if you look at the sigma 1s2 and sigma star 1s2, there are two electrons each. If you calculate the bond order, it becomes 0. Because the number of electrons in the bonding atomic orbital and antibonding orbital is the same, when that happens, the bond order becomes 0. Same is the case for the sigma 2s2 and sigma star 2s2. So in order to calculate bond order, we need not count all the electrons in the bonding orbital and all the electrons in the antibonding molecular orbital. We can look at the outermost incomplete energy level and calculate the bond order. So in order to do that, if you count the number of electrons in the bonding molecular orbital, you will count sigma 2px2, pi 2py2 and pi 2pz2, which makes it 2 plus 2 plus 2 is 6. And there are two electrons in the pi star 2py1 and pi star 2pz1, so which makes it half into 6 minus 2, which is equals to 4 by 2 is 2. So the bond order is 2. There is a double bond between oxygen atoms, and that can be proved here using bond order. And the molecule is paramagnetic because it has two unpaired electrons. Now, on the other hand, if you decide to count all the electrons, you will still get the same answer. The number of electrons in the bonding molecular orbital here is 10, and the number of electrons in the anti-bonding molecular orbital is 6. So 10 minus 6 is 4. 4 divided by 2 is again 2. So you will get the same answer. The choice is yours. You can use one or the other method to determine the bond order of oxygen molecule. Now, there are certain exceptions. It is a good idea to familiarize yourself with exceptions. For molecules like B2 and C2, the following configurations are consistent with the magnetic moment studies. Like I said earlier, theories are useful only if it explains a particular observation. So, studying the magnetic behavior of boron and carbon has shown that we cannot explain its magnetic behavior using valence bond theory. And again, if you use the regular electronic configuration for this, it does not explain the magnetic behavior again. But on the other hand, it's consistent with an altered electronic configuration for the molecular orbitals because of internal repulsion between the atomic molecular orbitals that are formed. And we find that in the case of boron and carbon, this is true, and this representation of electronic configuration, switching of the sigma 2p x2 with the pi 2p y2 and pi 2p z2, where the energy levels of these orbitals are switched, which means pi 2p y2 and pi 2p z2 has lower energy than sigma 2p x2. So that's a change that you need to recognize in this exceptional configuration. And then studying the magnetic behavior, we had seen that boron, atomic number 5, total number of electrons 10, if you distribute them into the molecular orbital using the exceptional configuration represented here, will illustrate the presence of two unpaired electrons. Sigma 1s2 is less than sigma star 1s2 is less than sigma 2s2 is less than sigma star 2s2 is less than pi 2p1 is equals to pi 2pz1. Therefore, there are two unpaired electrons there, which makes the molecule paramagnetic, and therefore this configuration can explain the observation. On the other hand, carbon is diamagnetic because it does not have any unpaired electrons in it. On the other hand, if we use the regular configuration, we would have found that carbon would have been paramagnetic, which is not the case when we study the magnetic behavior of the molecule. So for that reason, we study the physical properties, then we try to interpret the properties using molecular orbital theory, in this case trying to explain the magnetic property, and this molecular orbital theory has been successful in explaining the magnetic properties of these diatomic molecules. We can also write molecular orbital configurations for heteroatomic molecules like nitric oxide and carbon monoxide. So that's it for now. This is how you can use the molecular orbital theory to explain magnetic properties of a lot of diatomic molecules, which we cannot otherwise explain using the theories that we had before this, like valence bond theory. That's it for now.